Hi, it is JIT UA Courses, and welcome to lesson number 16 of the .NET Developer series, in which we will cover the most relevant topics to becoming a .NET developer. So hit the subscribe button and bell to see new videos on our channel. Okay, let's go. In this lesson, we will learn about garbage collection and managing disposable objects with using Block. If this sounds interesting to you, don't hesitate and hit the like button. Garbage collector in .NET. In the Common Language Runtime, CLR, the garbage collector, GC or garbage collector, performs the function of an automatic memory manager. The garbage collector manages the allocation and deallocation of memory for the program. For developers working with managed code, this means you don't need to write code to perform memory management tasks. Automatic memory management can eliminate common problems such as forgetting to free an object and causing a memory leak, or trying to access memory for an object that has already been freed. Advantages. The garbage collector provides the following advantages. Frees developers from having to manually deallocate memory. Efficiently allocates objects in a managed heap. Collects objects that are no longer in use, cleans their memory, and keeps memory available for future allocations. Managed objects automatically get clean memory for their placement, so constructors don't need to initialize each data field, there's enough memory for everything. Provides memory safety by ensuring that an object cannot use itself memory allocated for another object. Basics of memory. The following list summarizes important CLR memory concepts. Each process has its own separate virtual address space. All processes on the same computer share the same physical memory in the page file, if any. By default, on 32-bit computers, each process has 2 GB of RAM virtual address space. As an application developer, you only work with virtual address space and never manipulate physical memory directly. The garbage collector allocates and frees virtual memory for you in a managed heap. The virtual address space can be fragmented. This means that there are free blocks, also known as holes, in the address space. When a virtual memory allocation request arrives, the virtual memory manager must find one free block that is large enough to accommodate that allocation request. Even if you have 2 GB of free space, an allocation that requires 2 GB will fail unless all of that free space is in the same address block. In short, you need a whole piece of memory, not with gaps, fragments, hence fragmentation. You may run out of memory if there is not enough virtual address space to reserve or physical space to commit. Virtual memory can be in 3 states. Free, the block of memory is unreferenced and available for allocation. Reserved, the block of memory is available for your use and cannot be used for any other allocation requests. However, you cannot store data in this block of memory until it is committed. Fixed, the memory block is for physical storage. Memory allocation. When you initialize a new process, the runtime environment, CLR, reserves a contiguous region of address space for the process. This reserved address space is called the managed heap. A managed heap maintains a pointer to the address at which the next object on the heap will be placed. Initially, this pointer is set to the base address of the managed heap, to the beginning. All reference types are placed on the managed heap. When a program creates the first reference type, memory is allocated for the type at the base address of the managed heap, from the beginning. When the program creates the next object, the garbage collector allocates memory for it in the address space immediately following the first object. As long as address space is available, the garbage collector continues to allocate space for new objects in this way. The process goes one after the other from the beginning. Allocating memory from the managed heap is faster than allocating unmanaged memory. Because the runtime allocates memory for the object by adding a value to the pointer, this is almost as fast as allocating memory from the stack. Also, because new objects that are allocated sequentially are stored continuously on the managed heap, the application can quickly access the objects. Freeing memory. The garbage collector's optimization engine determines the best time to perform the collection based on the allocations made. When the garbage collector collects, it frees memory for objects that are no longer being used by the application. It determines which objects are no longer used by examining application routes. Program routes include static fields, local variables on the thread stack, processor registers, GC handles, and the finalization queue. Each route either refers to an object in the managed heap or is null. The garbage collector can ask the rest of the runtime to provide it with information about these routes. Using this list, the garbage collector creates a graph that contains all objects accessible from the root. Objects that are not in the graph are not accessible from the root of the application. The garbage collector considers inaccessible objects as garbage and frees the memory allocated for them. During collection, the garbage collector checks the managed heap for blocks of address space occupied by inaccessible objects. As it detects each unavailable object, it uses the memory copy function to compact the available objects into memory, freeing blocks of address space allocated for the unavailable objects. After compacting the memory for the available objects, the garbage collector makes the necessary corrections to the pointer so that the root of the application points to the objects in their new location. It also places the managed heap pointer after the last available object. Everything that we don't need, we delete, everything that remains is moved to the beginning, and we set the pointer to the beginning of free memory. Memory is compressed only if the collection encounters a significant number of unavailable objects. If all objects in the managed heap have survived garbage collection, then there is no need for memory compression. To improve performance, the runtime allocates memory for large objects in a separate heap, large objects heap. The garbage collector automatically frees memory for large objects. However, to avoid moving large objects around in memory, this memory is usually not compacted. Garbage collection conditions. Garbage collection occurs when one of the following conditions is met. The system is low on physical memory. This turns out to be an out-of-memory notification from the OS, operative system, or using a host, process. The amount of memory used by the allocated objects in the managed heap exceeds the acceptable threshold. This threshold is constantly adjusted during the execution of the process. The GC collect method is called. In almost all cases, you don't need to call this method because the garbage collector runs continuously. This method is mainly used for unique situations and testing. The GC algorithm is based on several considerations. It is faster to compact memory for a portion of the managed heap than for the entire managed heap. Newer objects have a shorter lifetime, while older objects have a longer lifetime. Newer objects are usually related to each other and are accessed by the program at about the same time. Garbage collection mainly occurs during reclamation, processing in search of dead, non-permanent objects. To optimize garbage collector performance, the managed heap is divided into 3 generations, 0, 1, and 2, so it can handle long-lived and short-lived objects separately. The garbage collector stores new objects in generation 0. Objects created early in the program's life that experience garbage collection are promoted and stored in generations 1 and 2. Since it is faster to compress a portion of the managed heap than the entire heap, this scheme allows the collector to free memory only in a particular generation, rather than freeing memory for the entire managed heap every time it does a collection. Generation 0. This is the youngest generation that contains short-lived objects. An example of a short-lived object is a temporary variable. Garbage collection happens most often in this generation. The newly allocated objects form a new object generation 0. However, if they are large objects, they fall into the large object heap, objects more than 85,000 bytes, sometimes called generation 3. Generation 3 is the physical generation that logically collects as part of generation 2. Most objects are removed during garbage collection in generation 0 and do not survive to the next generation. If an application tries to create a new object when generation 0 is full, the garbage collector performs a collection in an attempt to free up address space for the object. The garbage collector starts by checking objects in generation 0, not all objects in the managed heap. Usually the Generation 0 collection often frees enough memory for the application to continue creating new objects. Generation 1. This generation contains short-lived objects and serves as a buffer between short-lived objects and long-lived objects. After the garbage collector performs a Generation 0 collection, it compacts the available objects and moves them to Generation 1. Since objects that survive collection tend to have longer lifetimes, it makes sense to promote them to higher generation. The garbage collector does not have to recheck objects in Generations 1 and 2 every time it collects Generation 0. If the Generation 0 collection does not free up enough memory for the application to create a new object, the garbage collector can collect Generation 1 and then Generation 2. Generation 1 objects that survive the collections go to Generation 2. Generation 2. This generation contains long-lived objects. An example of a long-lived object is an object in a server application that contains static data that lives for the duration of a process. Objects in Generation 2 that survive garbage collection remain in Generation 2 until they are determined to be unavailable in a future collection cycle. Objects in the large object heap, sometimes called Generation 3, are also collected in Generation 2. Garbage collection occurs in certain generations according to conditions. Collecting a generation means collecting the objects of that generation and all its younger generations. Generation 2 garbage collection is also known as full garbage collection because it collects objects in all generations, all objects in the managed heap. Before garbage collection begins, all managed threads are suspended except for the thread that initiated the garbage collection. The following illustration shows a thread that initiates garbage collection and causes other threads to suspend. Work with resources. Finalize versus dispose. Unmanaged resources. Most of the objects used in C# programs belong to managed or managed code. Such objects are managed by the CLR and are easily cleaned up by the garbage collector. However, at the same time, some objects use unmanaged objects, connections to files, databases, network connections, etc. Such unmanaged objects refer to the operating system. The garbage collector can handle managed objects, but it doesn't know how to remove unmanaged objects. And here the developer must implement the cleaning mechanisms at the level of the software code. The release of unmanaged resources involves the implementation of one of two mechanisms. Creating a destructor. Implementation of the system.idisposable interface class. Creating destructors. If you've ever programmed in C++, you're probably already familiar with the concept of destructors. A destructor method has a class name, like a constructor, preceded by a tilde. Destructors can only be defined in classes. A destructor, unlike a constructor, cannot have access modifiers and parameters. At the same time, each class can have only one destructor. For example, let's define the simplest destructor in the card class. In this case, for demonstration, the destructor simply outputs a line to the console, notifying that the object has been deleted. But in real programs, the logic of freeing unmanaged resources is embedded in the destructor. However, during cleanup, the garbage collector does not call the destructor, but the finalize method. This is because the C# compiler compiles the destructor into a construct that is equivalent to the following. The finalize method is already defined in the base object class for all types, but this method cannot be easily overridden. And its actual implementation occurs through the creation of a destructor. Using the card class in the program, after its completion, you will see a message on the console about the deletion of the object. Note that even after the test method completes and the reference to the card object in the heap is removed from the stack, the destructor may not be called immediately. Only after the completion of the entire program, the memory is guaranteed to be cleared. However, starting with .NET 5 and later, destructors are not called when the program terminates. At the memory level, it looks like this. When placing an object on the heap, the garbage collector determines whether this object supports the finalize method. If the object has the finalize method, the pointer to it is stored in a special table called the finalization queue. When the moment of garbage collection comes, the collector sees that this object should be destroyed, and if it has a finalize method, it is copied to another table and finally destroyed only on the next pass of the garbage collector. The exact time of the destructor call is not defined. In addition, when finalizing two linked objects, the order in which the destructors are called is not guaranteed. If object A keeps a reference to object B, and at the same time both of these objects have destructors, then for object B the destructor can already work, while for object A the destructor will just start working. And here we can face the following problem. What if we immediately need to call the destructor and release all the unmanaged resources associated with the object? In this case, we can use the second approach, the implementation of the iDisposable interface. iDisposable interface. The iDisposable interface has a single dispose method, in which unmanaged resources must be released when the interface is implemented in the class. See this example. This code uses the try-finally construct. Essentially, this construct is functionally equivalent to the following two lines of code. But the try-finally construct is better to use when calling the dispose method because it ensures that even if an exception occurs, resources will be freed in the dispose method. General guidelines for using finalize and dispose. The destructor should be implemented only in those objects that need it because the finalize method greatly affects performance. After calling the dispose method, it is necessary to block the call to the finalize method on the object using gc.suppressFinalize. When creating derived classes from base classes that implement the iDisposable interface, you should also call the dispose method of the base class. Prefer a combined pattern that implements both a dispose method and a destructor. Block using. The C# syntax also offers a synonymous construction for automatically calling the dispose method, the using construction. The using construct formalizes a block of code and creates an object of some type that implements the iDisposable interface, in particular, its dispose method. When the block of code ends, the dispose method of the object is called. Importantly, this construct applies only to types that implement the iDisposable interface. But it is important to remember that using is just syntactic sugar, that is, a relief for the programmer. The compiler unfolds it into a try-finally structure with a dispose call in the finally block. This is all for this lesson. Thanks for watching. Hope you enjoyed it. Don't forget to subscribe to the channel and hit the bell so as not to miss the following videos in the series. Feel free to leave a comment and like this video. You are also welcome to leave any questions in the comments section. I will be happy to answer them. And also I encourage you to help brave people in Ukraine to defend themselves in this horrible war. Please use the QR code or links in the description to visit charitable foundations that help Ukraine. Thanks. See you in the next videos.